In this video, we're going to start to look at protein secondary structure. And secondary structure is due to the peptide bond or the peptide group and its general inflexibility. We're going to look at the common types of secondary structure, including alpha helixes and beta sheets. We're going to look at fibrous proteins. And we're also going to see that not all proteins have this regular secondary structure. So let's just look at the four types of protein structure. In the last videos, we were talking a lot about primary structure, which is just the sequence of amino acids. Here we're going to look at secondary structure, and you can think of secondary structure as regular polypeptide folding patterns. That is, small areas of consistent folding patterns that we see in a lot of proteins, and these include making a helix or making a sheet or having sharp turns in your protein. We call these secondary structures. First, we need to understand the peptide bond better if we want to understand secondary structure. So here is the peptide bond. So here's one residue's carbon alpha. Here's another residue's carbon alpha. And the way you connect amino acids is through this peptide bond. Now, you can see that this carboxylic group, is in a double bond. This actually has a resonance structure where the double bond can be between the carbon and nitrogen. And this happens about 40% of the time, and this other conformation is about 60% of the time. What that means is, since you have partial double bond structure here, you cannot rotate around this bond. This bond is rigid. And that means that the peptide bond actually has two conformations it's generally in. If your side chains are pointing in different directions, we call that trans. If, on the other hand, if this carbon alpha was up here and the side chain was pointing up, that is, it looked like this amino acid but on the other side, we would call that cis conformation. And the majority of proteins are in this trans conformation. Your one exception being proline. 10% of proline residues are actually found in the cis conformation, but everything else, it's going to be in this trans conformation. Now, when you look at a polypeptide chain, and you want to think about secondary structure, you're mainly looking at the backbone, or what you might also call the main chain. So when people say protein backbone, they're basically saying everything that's not the side chain. And to talk about backbone conformation, we have what are called dihedral or torsion angles. And a dihedral angle is an angle made up of 4 points. So when you talk about protein secondary structure, we have two different points that we talk about. We talk about the phi angle and the psi angle. And so the phi angle is between carbon 1, so carbonyl carbon of amino acid 1, nitrogen of amino acid 2, carbon alpha of amino acid 2, and carbonyl carbon of amino acid 2. This bond is free to rotate, so really when you're rotating this bond, you're looking at the angle between the carbonyl carbon of amino acid 1 and the carbonyl carbon of amino acid 2. What angle do they make? And I'll show something in class to better visualize that for your visual learners out there. And the other angle is the psi angle. You have nitrogen 2, carbon alpha 2, carbonyl carbon 2, and nitrogen 3. This can also rotate around the carbon alpha and carbonyl carbon, and here you're just measuring the angle between nitrogen 2 and nitrogen 3. Now with dihedral angles, you have all 360 degrees to work with. So you generally measure from 180 to minus 180 or 0 to 360. Different people measure in different ways. But with these fine psi angles, that's how we talk about a secondary structure or a localized 3D structure. Now, when it comes to fine psi angles for proteins, we can make what's called a Ramachandran plot. A Ramachandran plot tells you what phi and psi angle combinations are allowed and which ones are disallowed. And here we see a disallowed conformation because what happens is that you have steric hindrance. Atoms are overlapping. That's very energetically unfavorable, and so amino acids won't adopt that. So if you look at the Ramachandran plot where we have phi versus psi, we have some regions that pop out. So blue regions are generally very favorable. Green regions are tolerated. White regions are unfavorable or impossible. And when you do this, make Ramachandran plots for a lot of proteins, you see some patterns happening. And the patterns tell you secondary structure. So if your fine psi angles lie in this region, that means you have a right-handed alpha helix. If your fine psi angles, dihedral angles, fall in this region, you have a left-handed alpha helix. If they fall in here, you are looking at collagen. And if they fall up here, you have beta sheets, either parallel or anti-parallel. Now, something to keep in mind for Ramachandran plots is that since we're measuring backbone torsions, and the flexibility of the backbone depends on the side chain because of steric hindrance, different amino acids have different allowed fine psi combinations. This, what we're looking up in the top left, this is just a combination of amino acids or the most common plots. But if you look at glycine here, you can see for the fine psi plot of glycine, you have a lot of regions that are accessible, and in the middle you are not. Alanine, you have some flexibility as well because your side chain is only a carbon, but not as much flexibility as glycine. And proline, where your side chain is actually bound to your own nitrogen, or backbone nitrogen, you have a lot of regions that are not allowed. In fact, proline will adopt only really 2 positions often, everything else not that often. So now that we looked at backbones, we looked at Ramachandran, let's actually get into the types of secondary structure we'll see. And one of the most common is your alpha helix, which looks like this. It's a helix, and here is your space-filled model. In the alpha helix, it is generally going to be right-handed, although you can have left-handed. And for every complete turn, you go 3.6 residues. So every one turn of the helix is 3.6 residues. The pitch, or the distance between a complete turn, is 5.4 angstroms. And in general, your average length of the alpha helix is 12 residues, or 18 angstroms. Now in the alpha helix, if you look on either plot, you'll see that in the middle here we have our backbone atoms. So the backbones are buried inside an alpha helix, and they are connected through hydrogen bonds. And the hydrogen bonding is quite regular in that you'll have hydrogen bonding with the N residue and the N plus 4th residue. So what that means is if you're looking at residue 2, 2 would be your N, so you put the 2 in for N. It will hydrogen bond with residue 6, and it's always between the carbonyl carbon and amide nitrogen, where you have this nice continual hydrogen bonding network. For the side chains are pointing outwards from the helix, and they can point downwards as well. So that's your basic alpha helix structure. The other type of common secondary structure are your beta sheets. Here, they actually form in sheets, and you have 2 types. You have anti-parallel, where on one side you're going N to C, and the other side you're going N to C in the opposite direction. Parallel is where your N to C and N to C are running in the same direction. And these sheets, they're parallel to each other, and so people often call these pleated sheets. And between the sheets, like in alpha helix, you have hydrogen bonding between the carbonyl carbon and amide nitrogen. And if you look at the actual hydrogen bonding, you see that anti-parallel has straight up and down hydrogen bonding, while parallel is more slanted. This means anti-parallel is actually stronger or more favorable. They have stronger hydrogen bonds. On average, beta sheets can be 2 to 22 strands, average of 6 strands. Each strand generally has 15 residues, average of 6 residues per strand. So here are some different representations of the sheet. Here we have our space filling model. What you can see here, the purple are your side chain designations. So on the beta sheet, the side chains actually point away from the strand, so they're pointing outwards. And they go one pointing outwards to the left here, then the other one to the right. So they alternate how they're pointing out. To represent a beta strand, you use these arrows, while alpha helix you will use these ribbons. That's how you can show beta sheets and alpha helixes in proteins. Now, to connect these secondary strands, that is a term we call topology. So topology is how you connect things. And so for beta sheets, if you have an anti-parallel beta sheet, connection is relatively easy. You can have this small, tight turn. For parallel beta sheets, it's a little more difficult to have a turn, so you have to usually loop above and over or under and over to have this connection. And these turns, these tight turns, we have a name for them. And they're usually called reverse turns or beta bends. And it's just a very sharp turn in protein direction. As you can see, this is an extremely sharp turn. And here is our image of our beta turns. And we have two different types. We have a type 1 turn and a type 2 turn. But both types are only 4 amino acids, and you have this 180-degree turn. So if we look at type 2, if we look at residue 1 and residue 2, you can see that the oxygen of residue 2 is directly interacting with carbon beta of residue 3 here. I have residue 2, I'll be sure to change that. Now, residue 2 is actually usually proline in both types, and so that proline is helping make this type turn. And type 2 residue 3 is usually a glycine to help with this crowding. Since you have this oxygen here, if you have a glycine here, you just have a hydrogen and you don't have any steric hindrance. And that's it for this video, and I will see you in the next video.